here. All right, let's get started. Any questions about anything? You guys aren't affected by the Monday holiday, but at least you have Memorial Day off. But class will be as usual. And then, like I said, next week, week 9, I'll probably hand out your take-home final exam probably on Thursday. So you can have ideally, the weekend and then all of week 10 to work on the exam. All right, so let's continue up with our chapter. So again, we're just kind of appreciating these different types of ligands and how they bind. And so we have what are called chelating ligands. Sometimes you can also refer to them as polydentate. So polydentate just meaning that they attach on at several points. And so we have a few examples here. And so this is, again, just another common ligand here, this oxalate ion. And same thing with our amine. And so both of these are going to be donating 2 electrons to the bond. So that's very clear in our amine here. So again, they're donating to our metal. And so this is kind of the idea of how these ligands work. And there's a lot of frameworks, again, that follow this. Just trying to pull up some more publications. But obviously this framework is popular, again, this bidentate. And so sometimes you also see it, because this is a cyclohexane backbone, but you'll also see it with just the phenyl ring backbone. And then sometimes there's an extra arm here too, so this is commonly known as, again, like a pincer ligand. And so this would be abbreviated like PNP. And you might also have something else here that could coordinate. So like silicon, germanium, carbon. So there's lots of like carbene research, which, yeah, you could pull up a bunch of papers. And then usually, so we have platinum here, so then this would go on to stabilize some sort of metal potentially. Man, I don't know why the search is insanely slow. I've been like trying to pull up publications and like nothing's loading. So as long as the stream health is okay. And so also we have these tridentate. So of course bidentate would just mean that it connects at 2 points. Again, at those 2 nitrogens. This tridentate ligand, these start looking like crown ethers now. So tridentate means that it has 3 points of attachment. So you could put some sort of metal in the center here. And so let's just look up some crown ethers. And so crown ethers do the same sort of thing. So let me just show you what a crown ether is. At least this one loaded. So crown ethers are just something that looks like this, right? Repeating hydrocarbon and oxygen backbone. So this is 18 crown 6 for the number of carbons and then the number of oxygens. And so this is shown here with potassium. And so sometimes crown ethers are used to kind of bind like ions like we're seeing here. I don't know what's going on. And there's much other crown ethers that can be used to kind of capture and stabilize things. And then people also try to throw metals on there or make ligands kind of based off of these crown ethers. So lots of options for ligands. Other things we can talk about. So I think I mentioned CP. So CP is another type of ligand. Well, I mentioned ferrocene, that's what I mentioned. So we had discussed ferrocene, which is a sandwich complex. So it's iron, and then CP is this 5-membered ring that is aromatic. So it's often just drawn like so to show the aromaticity, because there's a charge on there. And then it has a bunch of H bonds. So again, it looks just like benzene, or pretty similar to benzene, just 5 instead of 6. And so ferrocene, oops, is this complex, if I could draw it, like so. And so ferrocene is interesting in that this CP ligand donates 5 electrons. So donates 5 electrons, and then it's bound, what would be 8 of 5. So meaning it's attached at 5 points. And this is, again, kind of beyond the scope of this course, but this is known as an L2X ligand. And so that's how you get to 5 electrons, since L is 2 and X is 1. So it's a mixed type. But like I said, this is kind of more advanced. Just you'll see that classification.
So how do you define a coordination position?
Rephrase the question.
What's a coordination position?
I still don't understand, like, in relation to what?
So I'm reading the polydentate ligand section in the book,
Mm-hmm.
and they're talking about a coordination position, and the definition is defined by what a coordination position is. But I was wondering what that is.
I mean, I would have to look at the textbook to look at the exact context, but it's probably referring to like cis and trans type nomenclature, or it's referring to this eta thing that I was trying to write here, but I'm being a little pregnancy brain, honestly. Right, we can also look at, like I said, I'm not sure what you're referring to, but you can also have different binding motifs with like alkenes. So for example, they can bind like end on like so. And so this would be like eta 2, or it's donating 2 electrons. So that's kind of weird, right? You don't typically have side-bound complexes. So I'm not sure if I answered your question, but kind of the point is there's a lot of different binding motifs, right? And like that's what we're getting at. We're only looking at like a small taste of inorganic chemistry, right? So all of inorganic chemistry is metals on ligands, and defining, right, how these things are coordinated. Because like we were looking at, even with this ferrocene, normally it's 8 of 5 coordinated, but once you start reducing it or oxidizing it, you know, it could bind in a different motif, and you know, then it will only be like half bound. But all right, so we could go back to this because, like I said, we could get lost looking at examples. I can pull up more examples, especially if my computer was faster, at least the internet. So let's take a look, though, at some of those geometric isomers. And so, again, that might elucidate some of your questions. And so we have our geometric isomers. And so, again, I think you've kind of played around with some of these in lab. And so kind of the point, too, and again, like back to maybe what you're asking, is depending on our geometry, right, then we have different potential isomers. So that's what you were playing around in lab with our structures. So now we're looking at these two examples here. And of course, the significance is that it has a square planar geometry. And then like y'all, we're playing around in lab. So either the two groups that are the same could be next to one another. So obviously on this side or on this side, right, symmetric. And they would be called the cis platinum isomer. And so, right, you could purchase these compounds. So these are probably commercially available, this diamine dichloroplatinum. And so that would be the distinction, right? You have cis diamine dichloroplatinaum 2, or you could buy the trans version where they're the two substituents are across from one another.
Is it in the square planar because it's the D8 formation?
Yes and no. So typically speaking, you're correct. And like, so this starts to get into like more in-depth in organic chemistry and like recognizing those trends. Again, that's like beyond the scope of this course. But yeah, that's like actually a common thing that happens. So of course, notice this is a coinage metal, or not coinage, our workhorse, group 10. And so these are typically good catalysts in among themselves. And so, yeah, they're, what did you said?
Well, I noticed that this also is on question 3. It's the same molecule.
Oh, yeah.
As I was doing it, I did it in the tetrahedyl form, and I was like, this doesn't make sense. And then I saw that you're doing that up there. It's in the square planar, which makes more sense. So.
Yeah, and so this, we'll touch on this. So this goes back to like the D arrangements and like what's kind of popular. So yeah, group 10 compounds, especially in the 2+ oxidation state, do tend to be square planar. But we'll get into that just a little bit, right? Because it has to do with like the d orbital splitting and then what's favorable. So that's what drives the geometry. And so I also have that. I made out the little molecules. Just let me switch. So I just showed them. Again, you can pass them around if you want and look at them. Oh my gosh. Sorry. My computer is just being a little wonky today. This is why I don't like using my personal computer. Awkward. I don't know what's going on. Right. I think we're back. If you're online, just let me know if we're still going okay. All right, so then we saw that we have a similar sort of thing for our octahedral complexes, where we have different isomers. So we have a few different combinations, right, of potential isomers. So we have, if it's just two different substituents and it's 2 and 4, again, we can have our cis isomers, and typically, right, that they're on that square planar axis, again, next to each other. And then versus our trans isomer, where again, they're going to be along that z² axis, so the principal rotation. And so then part of what we want to look at is why is this important? And so I try to pull up a paper. to show, again, the distinction, because that's part of the relevance. And so unfortunately, a lot of this chemistry is old, of course, distinguishing between these isomers. And so this is a 1954 paper, so looking at some cis-trans isomers of cobalt-3. And so we can look at what compound it is. So pretty similar actually to the platinum one that we've been discussing, so we can decipher the name. So they're looking at the cis and trans dichloro. So right, same thing, ethylene diamine. So ethylene diamine, right, just refers to this ligand. So we're just looking at a simple cobalt compound of that. So as you can tell, right, pretty common ligand. And blah, blah, blah. So this kind of gives you a sense too, at least like how they're prepared and calculated in the different like analysis. And so of course you can first of all see that no one ever gives you the synthesis very readily. So this is one of the challenges of grad school is you'll be tracking down old synthesis potentially for transition metal compounds. And then this calculated, this analysis, this has to do with elemental analysis. So we talked about elemental analysis briefly, like first quarter, but again, this is just kind of reminding you why that's important. It's used, right? It's reported in a text, and so that's a good technique, again, to verify that you made something. And so then the point of the paper is they were looking at the IR stretching frequencies, right? So measuring the difference in absorption. And so what's cool about the cis and trans isomers is they have different stretching frequencies, so you can distinguish them by a lot of different methods, but IR spectroscopy is one of the ones more commonly used, and it's pretty accessible. You know, IR is relatively simple there. So again, we're just kind of appreciating that these two different forms, again, have different stretching frequencies, and we could relate that all back to the orbitals, right, and those different energy levels. So all that is related. Sorry, I'm just a little slow since I have too many windows on my computer. All right, so that's one form. And then we said we also have these other types of isomers for our, again, octahedral complexes. So we're only focusing, again, on our square planar and kind of octahedral complexes. And so your book has a funny, at least I thought it was a funny term. I've honestly never seen this until your book. And so your book refers to this one as the cis isomer, or I've only seen this term, the FAC, so kind of like facial is the way I've come to think about it. And so now if we go to our little diagrams over here, so kind of the facial one sits, so you can kind of rotate it right such that all three of the same substituents are on the bottom. So I have that there. And then our other one is our MER isomer. And again, your book refers to it as a cis-trans isomer, so you can see how they got that name, right? One is cis, the other is trans. But again, I have not seen that terminology in my experience, and instead they're usually referred to as the MER isomer. And so the MER, you can tell because they're all on the same plane there, so you can draw a plane between all those three of the same substituents.
Do you have a preference on how to label it? Do you want us to do the cis or the cis-trans versus the base?
I mean, I probably prefer FAC and MER, but that being said, right, I can recognize either one. And it's more for y'all because, you know, like I said, I haven't seen this cystis a lot, like professionally, so probably you'll see the FAC and MER a lot more. And so then other isomers, so again, this may or may not be the answer to the question you were looking for, is again, right, you can have different binding motifs. And so this is all that is illustrating. So we have NO2, and it could potentially bind at the nitrogen, or it could bind at the oxygen. And right, again, you'd have to have some way to distinguish them spectroscopically, so probably some sort of IR frequency would be easy.
I think my question was more in regards to gelation and polydentate ligands.
Yeah, but even so, right? So then there's like a bajillion binding motifs that we could go through, and like I could pull examples till we're like all blue in the face of like, so basically you have tripodal ligands, right? Bidentate ligands.
Does that just mean the ligand attaches to two different places?
Yeah, so that's right what we had covered over here with the bidentate. So right when your ligand binds at 2 points, tridentate when it's at 3. But like I was trying to express, right, we can have it bound in a whole bunch of different manners depending on the ligand. So that's where the fun is. I mean, that's where I think the fun is. But again, I'm biased because that was my area of research, is this. And so then, again, we have our optical isomers. And so optical isomers, we should just define as non-superimposable mirror images. And so kind of the easiest way to draw it is, you know, pretend that there's a mirror here. You draw one isomer and then, right, literally kind of flip it as if there were a mirror so that you get, again, the chiral molecule. So again, you can think about your hands, how they're non-superimposable mirror images. And again, I advise molecule kits to help you with this. So definitely, right, this is why I have so many opinions on molecule kits, right? I have like all the kits and all the variations. So if you want to play with them, borrow them, that's all helpful. All right, so now let's get into crystal field theory, or at least a little bit of it. Again, this is starting to explain kind of why things take the shape that they take, why things are colored the way that they're colored. And so now let's look at what this is telling us. And so again, this is our representation of our ground state metal, right? We had talked about iron or any other metal, it doesn't matter. And then of course in the gas phase, because that's how most of these computations work. And so again, we are reminded that before they're bound to anything, so again, free metal, these d orbitals are all degenerate, aka they're the same energy level. But then once they become bound in a compound, they split. And so again, we're not going to get all into the nitty-gritty of these orbital diagrams. But again, we're just kind of building upon our fundamentals of our little bimetallic complexes. And so what I want you guys to appreciate too is why this is split like this. And so what we're looking at when we look at this is, so these are essentially, right, our non-bonding ones are down here. And then our bonding ones, because really what we're looking at here is our anti-bonding orbitals that have been pushed up. So these are, obviously we have our ligand-centered ones, or maybe not obviously, I shouldn't say obviously. This is complicated stuff here. But we have, you know, somewhere down here is where our ligands are bound, right? Appropriate energy levels somewhere. And then this is, of course, the antibonding that we're looking at. And then we're looking at the split here. So we're seeing how this is split. And then, of course, again, this is going to translate to colors and energy, right? So we'll have electrons too filled in here. All right, so let's start getting a little bit more specific. And now let's draw out our octahedral. So this is, I should have labeled this. So this is octahedral. So this is how it splits for octahedral. And again, we just want to start to appreciate it. I know that this stuff is dense. Believe me, as an undergrad, I would just like write whatever scribbles of orbitals and hope that it was correct. And so let's just kind of see why it's these ones. So of course we sketch out. So now I'm just sketching out what would be our ligands, so L6. And again, this is kind of beyond the scope of this course, right? Because you have a whole course devoted to inorganic chemistry and this, and coming up with what's called the irreducible representations and making MO diagrams. But we just want, like I said, a basic understanding. And so again, if we remember, this is our Z squared. And so of course that's why this is higher, because okay, it's bonding here. Like I said, right, we have our bonding ligands orbitals down below, but we're not looking at that right now. Okay, so the Z squared, that's why that one went up. And then we have this X squared minus Y squared. So if you remember, right, that's the one that's on the axis. And so that's why that one is up, right? So these are the two ones that are involved in bonding. And so pictorially, right, they match up. So right now, like I said, we're not getting into the math of it because we can prove this all mathematically, but we don't want to do that. We just want to look at it with the pictures right now and just see, okay, they line up there. And so then, like I said, we'll get into, so I got too excited and was just like colors. But this is really related to, right, our splitting energy. And so we'll have to think back to first quarter. Well, good thing the equation is here for us. So if we remember back to our electromagnetic spectrum chapter and relating, right, energy and wavelength, frequency, do you remember all that vaguely? So now it's come back to haunt us, but only slightly, right? And all we want to be able to do is, of course, relate the pretty colors back to the octahedral splitting energy. And so I put it in this form, so you remember, so it's also equal to, remember this is Planck's constant times the speed of light divided by the wavelength. And so that's, again, pretty colors where everybody gets excited there. So that's kind of, again, where we're going, and again, why the colors matter. And again, right, you can measure this with spectroscopy. You can get the millimeter length, calculate the energy, and then you can talk about all about the splitting field energy. And so then, right, same sort of thing. So going back to our basic concept of, okay, we add energy, electrons get promoted, and then we see pretty color. So same sort of thing, right? That's all we're being shown here, is this is our ground state. And then, again, we're focusing on these set of orbitals in particular because this is going to tend to be, right, like the homo-lumo, essentially. So, right, not always, but somewhere around here. So again, we're still we're still building up to the full picture, right? But again, we care about this because we care about all these things about whether it's high spin, low spin, how are the electrons filled up, right? Which one are occupied, unoccupied, because again, that tells us a lot of information. And then, of course, again, what's also significant and why people like transition metal chemistry is all these transitions tend to occur in the visible region. And again, right, compared to our organic molecules, thinking back to that TLC lab where we had to use the UV light to visualize it, again, all those, their transitions are in the UV. So that's why they're white and colorless versus, again, all these pretty compounds. And so again, just kind of an example of how we would start to look at this data. So now we have this octahedral complex, so titanium 3+ there, so we can tell titanium is in the 3+ oxidation state as well, since we have our neutral ligand. And okay, so right, they just did spectroscopy on it, and we see the absorption. And again, right, we're just seeing where it's doing the highest absorption. And so it's, again, probably exciting our HOMO, so exciting our d electron from our lowest energy set to, again, the higher energy set, kind of as hinted here potentially. And so then, right, we could work through this. So let's see, does it tell us the max absorption? So they didn't tell us our max absorption, but we can kind of guesstimate. So let's just kind of guesstimate. And so then we can ask, what is the octahedral splitting field energy? And so let's assume that the max absorption is 480 nanometers. I'm just kind of eyeballing there roughly. Again, if you were on the computer, right, you would do it much more precisely. And let me give you Planck's constant in case you forgot. So 6.626 times 10 to the negative 34, and I'll rewrite our relevant equations since it's been a minute. Don't forget the speed of light. Don't forget to convert that. All right, I'll give you all a second. Oh, electron volts, but what'd you use for Planck's constant then?
So, so I know HC is 1240 nanometers times electron volts. Something we learned in physics, and then I took the wavelength and I divided that. That cancels the nanometers, and you just left with electron volts.
So how many electron volts?
Sorry, 2.58.
So 2.58 electron volts, which So I had to look at the conversion. So 1 electron volt is 1.6 times 10 to the negative 19. So let's see. And then you can also let me know what other people got solving it with our joules unit while I convert this answer. So let's see, about 4 point. So that sounds about right. 4.19 or 13, sorry, I can't read, times 10 to the negative 19 joules, which, did we get something similar if we plugged it in with Planck's constant and stuff? So I'll plug it in on the calculator just in case. So 6.626 times 10 to the negative 34 times our speed of light. And then remember, we have to convert the nanometers to meters, and I'm going to be lazy and just put 480 times 10 to the negative 9. Of course, we could have done 4.8 times 10 to the negative 7. Oops, what did I do wrong? Let's just insert a parentheses. So either way, you should get about the same answer. So about 4.14 or 4.13 times 10 to the negative 19 joules there. Did we all get that?
That's what I got.
We good over here? All right, just making sure that that makes sense. And so again, right, this is good. We're just figuring out our octahedral splitting energy. Okay, so that again just tells us how large the gap is. And so then kind of the next thing that you'll want to characterize, or one of the many things you would characterize with transition metal complexes, is whether it's considered low spin versus high spin. And so part of what dictates this is, of course, right, how large the splitting is. So a smaller octahedral splitting field energy could mean that a compound has a tendency to be what's called high spin. And so let's look at what the heck we even mean by these terms. So low spin refers to the fact that you're going to fill up all your bottom lower energy orbitals first. So basically we're saying, right, it takes less energy to fill these bottom ones and pair them versus promoting an electron right to this higher energy. And so now with our high spin case, so high spin means that you would fill up all 5 first before you pair, right? So then in this case, so we have 1, 2, 3, 4, 5, 6 electrons. So you go 1, 2, 3, 4, 5. Since assumably, right, the splitting energy is less than perhaps right energy to pair or something. And then you go back and fill in the lower ones. So that's the difference between high spin and low spin. So again, both of these were D6s, right? So 60 electrons. It's just, again, how does it fill up? And so that's something that's kind of exciting too for chemists, right? Trying to make new compounds of high spin, low spin. Sorry, I lost the paper that I was going to show. Here it is. And so I just wanted to highlight this paper because this was a paper, this is back in 2015 now, but this was a pretty cool paper and made JAX because of this being an unusual compound. And so apparently high spin iron 1 compounds are pretty rare, and so that's kind of interesting. So this was one of the first high spin iron 1 compounds ever isolated. So that's again why people care and what we're trying to go for, at least again understand our basic trends here.
What's the relationship between the orbital occupancy and delta O, or octahedral splitting?
So just that, right? So we're trying to figure out, so if it's a large octahedral splitting, then it's going to tend to be low spin, right? Versus if it's a small octahedral splitting energy, it's going to tend to be high spin.
So spin is characterized by the length of that, as well as the number of orbitals that are occupying the top.
Yeah, so then, right, so going back to how you would characterize it, so we could say that this complex is diamagnetic. So those are some hints, right? So again, we're just taking an overview, but just the first distinction of whether something is diamagnetic or paramagnetic is, again, a good first step. So we can see that this is paramagnetic since it has a bunch of unpaired electrons, right? So paramagnetic. And again, right, that's just the first step spectroscopically. That being said, right, people again use computational chemistry. There's all sorts of other techniques to get like the actual spin state, like EPR, but again, those have limitations because only certain compounds can be looked at by certain techniques. All right, so then
I have one more question. Would these be two different orbital configurations that you'd see in the same element or two different ones?
so these would probably be two different compounds, right?
Okay.
So yeah, again, we weren't given details here, but basically these would both be D6 compounds just with different ligands attached. So now let's at least, again, we'll get a basic sense of these ligands, because again, we're looking at very like basic transition metal chemistry here. And so now we're kind of comparing these two. And so then we're just kind of looking, so let's kind of look and understand the similarities and differences. So, okay, these are both charged ligands, right? So they both have this -1 charge. And then, so that's the same. The complexes, right, both have a 4- charge, and it just so happens, so what's iron's oxidation state here? So they're in the same oxidation state.
+4. Is that, are you asking about the A? Yeah.
Yeah, look again, so that's a 4- charge overall. So remember, all these are -1.
So
Plus what?
It would be -10.
No, for your iron?
Yeah, I was thinking.
But it's -1, right? -1 times 6 is -6. And then x plus -6 equals -4.
Where'd you?
+2.
Yeah.
Oh, I see.
So iron is +2 in both of these. So iron 2 plus, iron 2 plus. Same D count, right? So then they would both be D6. So both have 6 electrons. And so now we can see, oh, there's a difference between them though. So one of these is considered low spin, right? So this is low spin, diamagnetic, since again all the electrons are paired, versus this fluoride where it's going to be high spin and of course technically paramagnetic. All right, so now let's try to understand what drives this. Again, we're only taking a simplified approach. We're not looking into it, but I mean, we could discuss it more later. And so what happens is, so again, these halogens or halides tend to be low spin, so they're considered weak field ligands. And so why that is because they just bind right with, they only have, again, this one electron, and so they just have right that one orbital to bond with. And so now we kind of go down the line. So these get weird. These are harder to predict, right, whether they're going to be high spin, low spin. It could depend on the compound. But these, right, tend to be now kind of L-type. They're neutral. Okay. But then as we keep going forward, there's something special about CO and cyanide. And so why they have this high spin is because they can bond in an extra way. So now let's look at our CO. If I can draw our CO quickly. So right, we have our CO here.
Wouldn't that form a double bond? No. I just thought nitrogen was the only one that formed triple bonds.
No, CO is a triple bond, remember? So that is its Lewis dot structure. And okay, so of course we have, right, this sp hybridized orbital, so that's doing bonding. But then we have to think about, right, those other orbitals, so our pi orbitals. So now let's kind of draw them. So of course we remember, right, we have our two pi bonds. So px we'll call them, and then py. And so what's special about these is, so now if we kind of look at these orbitals, especially if I had drawn them perhaps a little better, they kind of resemble d orbitals. And so that is what happens, is you have this essentially d-looking-ish orbital. Oh, and I'm screwing up all the colors. And so this is, again, I'm just trying to show one of our p ligands, and now it lines up with one of our d orbitals. So again, we're just appreciating that the colors are the same. And so all this means is that CO can do what's called pi back bonding. And so basically, right, not only do we have just our regular sp bond, right, going to the metal, our direct bond like usual, we have this through space interaction. Again, you can see how this is called a pi bond now. Again, it's through space, right? And so again, that extra bonding ability then is what makes these ligands strong field. So then again, because it can back bond, now it's really bonding, and then of course that's going to send this even higher in energy, right? So again, if it's even a better back bonder, then our anti-bonding are higher, and it's kind of hard to think about sometimes, but that's why these now are pushed higher in energy, because we have favorable back bonding, and so that's why these tend to have, again, a large octahedral splitting field, versus these simpler ones where we're just getting that direct sigma bond. So I'll just say more sigma bond, and again, right, pi back bonding. At least, again, just in general, this is our trend here. So yeah, on an exam, you'd probably only be exposed to these ligands that we've talked about if I was like asking this, right? Again, there's like a bajillion things that can be a ligand, so we're just going to focus again on our basic trends. Or I might ask you to just kind of like compare, right? What if this was a high spin? What if it was low spin? And what would it be, right? Diamagnetic, paramagnetic. So let's look at a few examples and see if we can predict. So we'll go a little bit over time, just so we can finish up this. So now if we have this compound, so now predict the splitting diagram. And so you want to draw it out right for your octahedral complex. So see if you can draw what that would look like. Again, based off of what we said too, that this is a strong field ligand. So then for this one, again, octahedral, right? They're always going to have the same splitting. I don't expect you to label them at this point, but, you know, again, it's always good to practice. So at least understanding which ones are involved in bonding, and then, of course, the other permutations, YZ. Who am I missing? Oh, XZ. And then, so what do we know about cyanide again? Is it a strong field, weak field ligand?
Tends to fill the lower orbitals first.
So lower orbitals, so that, right, strong field ligand then. So then we want to figure out, so then cobalt, what is the D count on it? What's cobalt's oxidation state here?
+3.
So cobalt +3, so then what does that make it D count wise? So what is it neutrally? Cobalt. Can turn around and look at the number, or I'll pull it up on P table, right? So we look at cobalt, what's the big number there?
No, it's the 27th element.
Not 27, this one.
Oh, okay.
Yeah, so it's D9, right? So we're saying that we want to treat it as D9, again, neutrally. So then if it's +3, D6. And so yes, we'll fill it up with the lower orbitals first, since again, strong field, so 1, 2, 3, 4, 5, 6. So we would expect this compound to again be diamagnetic. And so luckily for, if you were the chemist trying to distinguish this, it wouldn't be too hard to test, although that being said, this is not NMR active, but anyways. And so then let's try that. So what do we predict for cobalt F6 then? 3 minus. So strong field, weak field, what would that look like?
It's a weak field ligand, and it's in the +3 oxidation state for the cobalt.
So good. So weak field, so we can sketch that out. So again, right, pretty similar. So this could be what you are asked to do on your exam. Actually, you'll look at your exam. And then we'll fill it up 1, 2, 3, 4, 5, 6. So again, putting them in the higher energy before pairing them. And so now we can say, right, high spin as well, paramagnetic. And so again, you could at least tell them apart spectroscopically, right? And then again, you could compare the energy difference between them, what colors they are, and that would at least give you your octahedral splitting field energy. So that being said, right, a lot of inorganic chemistry is basically making these little diagrams, and then every geometry has a different arrangement. And then you see, right, does this match with the data that I'm getting? Is it paramagnetic? Is it diamagnetic? Does it match with how the electrons fill up? And then, like I said, right, there's a whole bunch of other more refined techniques that tell you, like, spin states, and then you do computational chem.
So what was the distinction that that determines how you filled in those orbitals? So you first filled in the dxy, dx, dxc. Is it because of the difference between the fluoride and the
Yeah. So in this case, right, we weren't given a lot of information. So we can only go off of this trend for the most part, right? So if typically, again, if you see the halides, you know it's going to be low spin versus like CO or CN, or again, they tend to do pi back bonding, then it'll be high octahedral, right, low spin. But, so again, like I said, that's how we would do it on the exam of like, right, I would just pick the extreme cases. But other ways you could phrase that on the exam is kind of like, this is the data that matches, right? It's diamagnetic, it's blah, so which one is it, right?
Is it a binary thing, like is that a low or high?
Yeah, so it's either low or high, right? And then again, that dictates like how many unpaired electrons, so that's where the computational chemistry comes into play, because it all has to match, right, to basically publish the paper, else you have no idea what's going on electronically. So that's where computational chem really does go hand in hand with this inorganic chemistry, because like, again, you'll sketch it out, this is what I predict, and then does the true data match that? And if it doesn't, right, again, you go back to the computational chem and try to figure out, like, where are my electrons? But usually a back of the envelope calculation is pretty good to, like, at least start getting the understanding. And then you use the computational chem to just, like, verify that and show the orbitals. But honestly, the computational chem can be hard to get correct. So you can, like, know what you're going for, and then it can take a while to tease that out computationally. All right, I think that's pretty much the end of this chapter here. So again, don't forget this energy equation either, because again, that will come up, right? How big is our splitting based off of our color?
Are we going to go into the Jean's Tushita spectrochemical series?
I mean, that's what this is.
That's all this.
Yeah. So right, that's all we're going into. But like I said, what we're really appreciating is we need data, right? We can kind of make all of these predictions. Yes, we have these trends, blah, blah, blah. But ultimately, right, you have to get a crystal structure, you have to get data, you have to draw out the orbitals and see that it all lines up. All right, so we'll stop there. So let me know if you have any questions online, and then we can take our break. I'll hand out our quiz. The hint that I'll give for number 4 is if you can't find the formula, you can always brute force these radioactive half-life equations. So number 4 could actually be brute forced. So right, you can just manually work out every half-life. All right, so I'll hand out the quiz. Feel free to take a break. And then I'll try to hand back some papers. I'm still a little behind on grading, but I at least have, I think there's quizzes.